Recall from the last section we learned a test called the alternating series test, which applies to series whose terms alternate in sign. Today we're going to look at series such as this one. This series is neither all positive nor alternating. There are 3 positive, 2 negative, and maybe 4 more positive, 5 more negative. In this case, the alternating series test does not apply. So what we're going to do is that we make a new series. We take absolute value of each term. So then we gain a new series with all positive terms. And if that series is still convergent, we say that this series is absolutely convergent. So that's our new definition, the first one. A series is called absolutely convergent if the sum of the absolute value of each term is convergent. The second definition says that if a series, it says a series is called conditionally convergent if it is convergent but not absolutely convergent. Here you may pause the video and work on example 1 from the text to get familiar with these 2 new definitions. All right. Let's look at example 2. Determine whether the alternating harmonic series is absolutely convergent, conditionally convergent, or divergent. Again, pause the video and work on it, and come back. All right. Let's look at the alternating harmonic series, which is this one. We learned from the previous section that the harmonic series, when all the terms are positive, is divergent. And from last section, we use the alternating series test. We know that the alternating harmonic series is convergent. And therefore, by the definition, we know that the alternating harmonic series is conditionally convergent because it is convergent but not absolutely convergent. Notice that here, if a series is all positive, then the 2 concepts, absolutely convergent and convergent, are equivalent. So there's no difference between being absolutely convergent or being convergent if a series is all positive. Now here you might feel that being absolutely convergent is quite strong, right? If you make a series all positive and still convergent, that's a very stronger condition than being convergent. And that's the next theorem, which says that being absolutely convergent implies being convergent. Now I have a question for you. Is the converse of this theorem true? In other words, is this true that if a series is convergent, then the series is absolutely convergent? I'm sure you can tell that the converse is not true. Now pause the video again, study example 3 from the text. And then next we look at 2 tests called the ratio test and the root test. These 2 tests are quite useful and students generally like them. They're easy to apply. All right, let's look at it. The ratio test says that we look at the ratio of 2 consecutive terms. takes absolute value of that ratio, and if that value has a limit, call it L. If that limit is less than 1, then the series converges absolutely. And if that ratio is greater than 1, then the series diverges. If the ratio equals 1, we don't get any conclusion. We're not going to look at the formal proof. However, we can still understand the proof intuitively. Let's see how come the ratio of two consecutive terms tells us whether or not a series converges or not. How come? Let's look at an example. This one. So here this series is 2 to the n over n factorial. So these are the terms. Let's look at the ratio of the n plus 1th term to the nth term. Pause the video here and do a quick calculation. Take the n plus 1th term and divide it by the nth term. The result, the ratio equals this after some cancellations. And this is actually less than or equal to 2/3 for n greater than 1. And this inequality is equivalent to this inequality. So each term is less than 2/3 times the previous term for all the n greater than 1. And now let's look at this series again. It's equal to 2, which is the first term, and 2, second term. The third, let's call that a sub 3 now, and a fourth, and here should be a sub 5. All right, since we know each term is less than 2/3 times the previous term, we rewrite a3 as less than or equal to 2/3 times a sub 2. And a sub 4 is replaced by 2/3 times a sub 3. And then a sub 5 is less than 2/3 times a sub 4, and so on. Next step, we keep the first two, keeps the third. Now a2 becomes 2. a2 equals 2. And then look at this one. 2/3 times a3 is less than or equal to 2/3 times a2. So we get an extra 2/3. And therefore has a 2 times the square of 2/3. And then you can imagine next has another 2/3. Look at this series. Does that look familiar? It's a geometric series with common ratio 2/3. And we know that geometric series is convergent if the common ratio is between -1 and +1. In other words, if the absolute value of r is less than 1, then the geometric series is convergent. And therefore, by the comparison test, we know the original series is convergent. So this one tells us something about a series when we know the ratio of any two consecutive terms. Let's generalize our observation. So whenever we know that the absolute value of that ratio has a limit that's less than 1, we can always make a new geometric series with ratio equal to that limit, right? And then we can use a comparison test to tell whether this series is convergent or not. And so that tells I hope you're convinced that the theorem, the ratio text makes sense, because we can always do the same thing like we do here. Alright, now pause the video and study these two examples. These are all good examples. And then the next test is called the root test. I'll let you study on your own, and then also work on example 6. The last topic, rearrange